Hello everyone, my name is Zifan Xu, a PhD student from the University of Texas at Austin. In this video, I will present our work, Dexterous Locomotion in Confined 3D Spaces with Reinforcement Learning. While RO-based locomotion controller has achieved great success in agile and robust movement on rough terrains, those rough terrains, however, only have constraints underneath the robots. For example, the figures show lag robots in both simulation and the real world. The environments are pyramids, rough surfaces, stepping stones, where only constraints from underneath the robots present. While a field prior work does consider constraints only from top, those environments are simple and handcrafted, limited their application to diverse and challenging environments with all-around constraints. Environments with challenging all-around constraints or confined 3D spaces requires a cyclic and asymmetric limb movements. For example, the agent has to step on the obstacle to adjust its body orientation in order to squeeze through the limited 3D space. While prior work in co-body planning has considered confined 3D spaces, it usually requires to design complicated systems, and the planning speed is relatively slow, which makes it hard to perform agile movement. The goal of this work is to explore the possibility of an RO-based locomotion controller that can perform agile and robust locomotion in diverse and confined 3D spaces. In order to train such a RO controller in the simulation, we need to design diverse and confined 3D spaces in the simulation. We propose tunnel environments, which has both ceiling and floor constraints represented by a pyramid matrix. Both pyramid matrices have the same number of rows nr and number of columns nc. Each pyramid is characterized by a tuple xyz lwh, representing the xyz coordinate of the center of pyramid bottom surface, and the length, width, and height of the pyramid. The tuple parameters are randomly sampled by some predefined random distributions, where the difficulty of the environment can be adjusted by NC, NR, and the randomness of the random matrices. We then present three different learning approaches. The task is to navigate a lag robot in confined 3D spaces to a given goal location xg and yg. The first approach is end-to-end dexterity. The RO controller is represented by a feed-forward neural network that takes as input of proprioception, flattened elevation map, gravity vector, and the relatively goal location. The reward is a goal-reaching reward that assigns positive 1 whenever the agent reaches the goal within some distance threshold range dg. An exploration reward is applied at the beginning of the training so that the agent's linear velocity aligns with the direction to the goal. Such an approach preserves the solution space for the agent to explore its own paths and motions to navigate in confined 3D spaces, but the training is sample inefficient. We then present a major approach, hierarchical dexterity. Instead of directly navigating to the global goal location, it uses a reactive path planner to plan a local goal body pose that is always 0.5 meters in front of the robot. Then the agent takes an input of local goal location instead of the global goal location. The reward is kept the same except for that the agent is rewarded for reaching local goal location. This approach allows the agent to explore its own motion but leaves the longer horizon path planning to a classical path planner. In the end, we also include the popular training strategy of parameterized motor skill, where the agent, instead of receiving local goal location, it receives the motion command that specifies the linear angular velocities, torso orientation planned by the same reactive planner. Then the reward encourages tracking of the command velocities and body pose orientation. This approach has least solution space that the agent has no freedom to explore even its own motion, only the appropriate limb movement to track the specified motion. Finally, we discuss the training configurations. We use semantic parallel training in ICRA. We created random tunnel environments with varying difficulty levels. The tunnel size is always 2.5 meters by 1.5 meters. But the number of rows in the pyramid matrix varies across different difficulty levels. For the three difficulty levels, easy, medium, and hard, the number of rows is 2, 3, and 4 respectively, and the number of columns is always 3. We use an R algorithm of PPO. Finally, we present our result. The major proposed approach, hierarchical dexterity, achieved the highest success rate across all three different difficulty levels. The parameterized motor skills achieves a decent success rate in easy environments, but the performance significantly dropped in harder environments. In terms of the sample efficiency, our hierarchical dexterity achieves the best sample efficiency and converges after only 40 million time steps. Not surprisingly, end-to-end dexterity uses the largest amount of 600 million time steps. Parameterized motor skill, while optimizing in least solution space, is not more sample efficient compared to the hierarchical dexterity. In this slide, we present the visualization in a simulation that compares the three different approaches in medium and hard environments. As we can see, hierarchical dexterity can successfully navigate through the medium and hard environment, while end-to-end dexterity and parameterized motor skill all stuck at somewhere in the environment. We summarize takeaway points in this work. First, the robust locomotion in confined 3D spaces only emerges in hierarchical dexterity by training to reach local goal location computed by classical path planner. Parameterized motor skills are not sufficient to navigate in confined 3D spaces. Generalizing to diverse and confined 3D spaces is still challenging. Thanks for listening to this video. Feel free to reach out if you have any questions.